Hi everyone, my name's Tim Roughgarden. I'm a professor in the Department of Computer Science at Columbia University, and the IBM Columbia Blockchain and Data Transparency Initiative has been kind enough to generously fund me through two different seed grants. One is a teaching grant to develop a new course. The other is a research seed grant with Chen and Christos Papadimitriou. And I wanted to take a little bit of your time today to just give you a brief progress report on each of those two grants. So let me start with the updates on the research side, and let me tell you about 4 papers that are either published or under submission or about to be submitted. And I'll just go through them one by one and tell you a little bit about each. The first paper, I think she and/or Christos will say a little bit more about, so I don't want to talk too much about it. That's an axiomatic approach to block rewards, and we published that paper in the AFT conference last year, which was in Zurich. So AFT is a new ACM conference. 2019 was the first edition of AFT, and it's really the main ACM conference where you would publish about blockchain at this point. So the AFT stands for Advances in Financial Technologies, which at least at the moment refers primarily to blockchains. So what we sought to do in this paper is give kind of a critical analysis of the way that block rewards are distributed in a proof of work blockchain such as Bitcoin. So the way it works is that block rewards are distributed proportionally to the amount of hashing power that each miner has. So if you possess 1% of the overall hash rates, you will in the long run be making 1% of the overall block rewards. And we wanted to take a step back and ask the question, is there anything else you could do that would be in some sense better than this proportional to hash rate rule? Or alternatively, maybe even more interestingly, could we say that the way it's done right now is optimal in some sense? And so the main result here is a uniqueness result. We propose a few axioms, for example, like payment should be non-negative, budget balance, they should sort of sum to a fixed constant. But then crucially, we have 2 axioms. One is Sybil proofness, saying that no one should be able to do better by splitting into multiple identities. And then we also had a collusion proofness axiom, which says people shouldn't be able to benefit by forming cartels. And we show that actually the current proportional rule is the unique way, the unique solution that satisfies all of those axioms. So, we were inspired here by the axiomatic approach from economics, like Arrow's impossibility theorem, ruling out non-dictator voting rules that satisfy a couple of natural properties, or, for example, Shapley's characterization of a Shapley value as the unique value in cooperative game theory that satisfies a given set of axioms. So that was the first paper. The second paper, my co-author is Clara Schinkelman, and she has a really nice pedigree. She was a PhD student of Noga Alon in Tel Aviv, and now she's actually joined a Bitcoin research startup called Chain Code, which is here in New York City. And so I think this is cool. This is going to be, I think, a really nice connection between Columbia and the group around me and local industry. Like I said, they're just located in Midtown, and they seem to be doing really interesting work. So what's our paper about? And this is submitted. This is under submission to this year's edition of AFT. Well, so again, we're going to take a critical look at again reward sharing schemes, but this time we're really thinking inside what are called mining pools. So in most blockchains where there are miners, like Bitcoin or Ethereum or whatever, miners prefer to sort of band together in groups, to join their computational forces and mine jointly to try to authorize the next block to be added to the blockchain. And then those miners distribute the rewards amongst themselves. Why do miners do this? Why do miners join mining pools? It's so that they can smooth out their rewards over time. Now the question arises, when a pool is successful and actually authorizes a block, and the pool earns itself a block reward, in what way should that be distributed to the mining participants? And the natural way to do it, and what people aspire toward, is they'd like to distribute those rewards internally proportional to how much computational power the different miners brought to the table. The next question is, how do you actually estimate the hash rate of all of the miners in a pool? Obviously, if you just asked a miner, hey, what's your hash rate? They'd be tempted to state you a number that's a little bit higher than reality. So you need some way of measuring how much computational power bring to the table. And usually that's done in a very clever way through an idea known as partial shares. Right? So the way that a proof of work chain like Bitcoin works is the way you successfully authorize a block is you sort of come up with a block, so you pick some transactions, you pick a nonce, And it should be the case that when you apply the SHA-256 cryptographic hash function to the block that you've come up with, the results should begin with a whole bunch of zeros. So currently, you basically want something which hashes under SHA-256 to a 256-bit string that begins with 80 zeros or more. This number 80 is a parameter that's automatically adjusted over time as part of Bitcoin's difficulty adjustment algorithm, and it's always sort of tweaked so that you expect one new block to be authorized roughly every 10 minutes. And so the clever way that most of the mining pools assess how much computational power each of its miners has is they say, hey miner, whenever you actually successfully come up with a block, okay, maybe it doesn't start with 80 zeros in a row, but if it starts with at least 70 zeros, 70 or more, go ahead and report that to us, and we'll take that as proof that you are working pretty hard to try to authorize a block. By the time somebody finds something that hashes with 80 zeros, that sort of ends the epic, a new block is authorized. You look back in time, you say, oh, well, how many, 70 zero blocks did we get from everybody? And then you distribute the rewards proportional to the number of these partial shares, proportional to the number of times that a miner came up with something with at least 70 zeros. And something that's been observed many times is that intuitively this seems to be throwing away information, right? Because really the rewards are only determined based on whether you cross this threshold of 70, when in fact you have richer information in the mining pool, right? You really know whether the block hashed to having 70 zeros in a row, or 74 zeros in a row, or 79 zeros in a row, or whatever. And so a natural question is, in what way could you use this more fine-grained information to have a mining pool which in some sense is better? And the main result in this paper, I think, is a little counterintuitive, which actually says there is no way to use that fine-grained information to have a reward sharing scheme which is better than the simplest one where you just sort of look purely at whether you cross the threshold of 70 zeros or not. Now, to say that something is better, you need some objective function, and so we just look at the variance that miners enjoy. So any attempt to use more fine-grained information will actually increase the variance that miners experience. And of course, the whole reason miners join mining pools is to decrease their variance, so we thought that was a natural optimality result. Next, I want to talk about a couple papers that are joint with Andy Lewis Pye, who's a collaborator of mine at London School of Economics. I'd summarize the aesthetic that we're applying to both of these papers. We're really trying to sort of refocus the discourse around blockchain protocol design away from kind of operational details, away from worrying about exactly how something works step by step, and really refocus on the mathematical properties that a blockchain protocol might or might not have. And then the kind of results we're after is, we might define some mathematical property A of a blockchain, like say something related to liveness, and some other property B, for example, related to security. And we might want to say, in fact, we do have a theorem in this first paper, which says you either have to pick property A, a type of liveness property, or you have to pick property B, a type of security property, and you cannot have both. Okay, so the main result of that first paper is an impossibility theorem. And then, so those are just two mathematical properties, and then you sort of look at the space of blockchains and you realize that the longest chain protocols are exactly the ones that satisfy property A, and the BFT-inspired protocols are exactly the ones that satisfy B. So longest chain, you're prioritizing liveness specifically when you have an unpredictable amount of participation, and when the BFT protocols, you're prioritizing security. But again, our definitions do not refer to a longest chain or to a BFT computation. Our definitions just refer to these mathematical properties that a protocol might or might not have. Our dichotomy theorem is in terms of those properties, but there's a natural interpretation of that dichotomy in the sort of leading designs in blockchains. The second paper with Andy also very much follows this aesthetic, where we basically start from mathematical properties and then ask to what extent does that dictate what the implementation has to look like. So does the implementation necessarily follow from the properties that you want? And specifically, a lot of the papers about, if you want certain security properties, do you have to look like a BFT type protocol like Algorand? And the way we formalize that in this paper is we introduce a notion of a certificate. And so one of the main results in the second paper says that really the only way you can get the kind of security guarantees that Algorand has. So in other words, you have security, you have no rollback of transactions, in a partially synchronous setting. The only way to get partially synchronous security is via this certificates route. So that's a sense in which the way Algorand solves the security problem in a partially synchronous setting, they did it in the way that you had to do it. They did it in a way by producing certificates. In other words, certificates are not just a sufficient condition to get security in a partially synchronous setting. One of these main theorems says it's also a necessary condition. Let me now move on to a progress report on the teaching side. So the C grant I was awarded was to develop a new course titled Foundations of Blockchains. And I will be teaching this a couple times in the next couple of years. I have not taught it yet, so I can't really tell you anything about what's happened in the past, just tell you sort of where things stand, what the course is about, and what I'm thinking for it. So why a course on the foundations of blockchains? Well, at this point, I think it's pretty uncontroversial to say that some form of blockchain technology will probably be around for a while, for a couple of decades at least. And so for that reason, it seemed like the time was right for an intellectually rigorous course, to give students the lay of the land, to give them mathematical tools to sort of reason about blockchain protocols. And then I also want to really, highlight opportunities for foundational research in the area. I really think this course could give Columbia students sort of a unique edge in doing innovative research in the blockchain space. So I definitely do envision it as a theory course, a graduate level theory course. So it's going to be intellectually rigorous. We will do math and proofs in the lectures, not all lectures all the time, but lots of proofs in the lectures. And the emphasis will be on mathematical modeling and analysis. So really in the spirit of the research papers I was discussing on the previous slide. And so accordingly, the emphasis of the course will be much less than sort of the application layer. I don't necessarily plan to talk that much about decentralized finance based on smart contracts, maybe a little bit, but that won't be the main point. Really, I want to focus, frankly, on the technology, right? So I really want it to be a computer science course where we just talk about how does this stuff work, how should it work, and what are the engineering challenges to make a next and better generation of blockchains. So certainly, my interests are very much on the game theory side, so I'll certainly discuss a lot about incentive issues, things like selfish mining and nothing at stake and proof of stake blockchains. I do want to cover a fair amount, several weeks worth of material in distributed computing, which is a topic which is often sort of missing from the course offerings at a lot of the top departments. And now, sort of classical distributed computing is really having a renaissance in the context of blockchains. So I'm going to talk some about classical consensus, stuff that we could have taught in the 90s, but I'm going to do some classical stuff just to give students the context to appreciate the innovations that have come along with blockchains. So for example, in what sense, does Nakamoto's consensus avoid all of the impossibility results that, that we thought we had in the classical world? Certainly, I want to talk about some of the major design issues, which again, my research papers on the previous slide touch on some of these. How should you even define proof of work versus proof of stake? And then what are the pros and cons of using each? Mining pool reward sharing, there's lots of nice research to talk about. I'll discuss that. Transaction fee mechanisms, I think is going to be a great topic. So Ethereum is in the middle of probably changing their transaction fee mechanism through a proposal known as EIP 1559. And I think that's going to be a pretty amazing case study to see sort of how a mechanism design problem arises kind of in the real world, kind of for really the second biggest blockchain. A sort of very crucial change is really a mechanism design change. So I'll certainly talk about that. And then scalability is another topic I'm definitely going to discuss. So how can blockchains sort of process enough transactions so they might legitimately be able to compete with, say, a MasterCard or a Visa. So some of that will be, so-called layer one stuff like sharding. I'll also certainly talk about payment networks, probably using the Lightning Network as a case study. And honestly, this field is moving so fast. I'll bet, something's going to happen. There'll be kind of an October surprise probably for my blockchain course where, some new cool thing comes out that I'll probably smuggle into one of the final lectures. So this is just to tell you a few of the things I'm sure that I'll be covering. This will probably only get us through maybe like 8 weeks out of 13, and so there'll be plenty of topics to fill in the remaining lectures. One thing I want to emphasize, I've always, for my graduate courses, I've always prided myself on trying to be as cutting edge as possible and present, really pretty recent stuff, but in a way that's, relatively accessible. But man, this course is going to be cutting edge in a way that I've never had to experience. And it's going to be a ton of work, but I think it'll also be a ton of fun, both for me and for the students. Like honestly, just in the last couple of months, there's been a couple papers that I will definitely be teaching as part of this course. And honestly, a lot of the good stuff is not even in research papers. A lot of the most important ideas and the attacks and so on, you'd find them on Reddit, or on Twitter, or on a Discord channel. So hopefully, one of the positive externalities of a course like this is it'll take some of this information, which is just distributed in all these sort of random social channels, and have them kind of part of a cohesive whole. That's definitely one of the things I want to achieve. So that's the vision for fall 2020 for this coming semester. A little bit terrified, but also pretty excited. I think it's going to be a lot of fun. So the hope would be that by the end of that second time, by the end of 2021, I would love it if this course was kind of well known throughout the blockchain community. If Columbia, was really known as a university that especially took a lead in education in this very important topic. So those are the ambitions. I think we can reach them. Wish me luck, and thanks very much for your time.
Hi, I'm Eric Johnson. I'm a professor at Columbia Business School, and I'm excited today to share with you some of our new research. I also direct the Center for Decision Sciences.
And I'm Colin Merkva. I'm a postdoc at Columbia, and we're excited to talk to you today about this research.
The thing we're going to talk about today is how you might increase adoption of exposure notification or contact tracing apps. And we want to thank, first off, DSI and IBM for funding this research. These are initial results, but we think they are actually very interesting. The background is important, though, and it is the notion that ideas about what privacy are actually assembled at the time of questioning. And that means the way we ask a question can drastically affect their responses. This is going to be particularly true when you're in contact tracing, because you're trading off future gains, being notified that you've been exposed to COVID, to short-term losses in effort and privacy. Obviously, contact tracing apps are interesting, but they're only one of many decisions you make about privacy. And we know from other work that actually the way the question is asked can change the decisions that people make. Here's some work that we did a very long time ago, just asking people if they wanted to be in future surveys, changing the phrasing of the question. And as you can see, the results range from 48% of the people saying yes to 96% of the people saying yes, depending upon how you asked. Now, this whole area is called choice architecture. And choice architecture essentially is a study of how small changes in the choice environment can influence decisions. And the important thing here is we're not changing the incentives in an economic sense or information. We're only changing how the question is posed. The goal of choice architecture is to encourage people to do what is in their own best interest if they really thought about it. And one of the most famous examples, sorry if I say so myself, involves organ donation, a paper that Dan Goldstein and I published in Science in 2003. If you look at the bar graph, you'll see a condition where people had to opt in to become an organ donor, which is a standard way of doing it in the United States, or opt out to not become an organ donor, which is a way it's done in about half a dozen different European countries. And here you see that there's a huge difference. Almost twice as many people are willing to be donors in the opt-out condition. The important slide here, and point of the slide in lots of ways, is the neutral condition. Here, people were forced to make a choice. And when they had to think about it, what did they do? Most of them decided they would actually want to be donors. So there are a lot of barriers to making decisions, particularly those surrounding novel environments like privacy, contact tracing, in the time of COVID. There are at least two barriers that I want to talk to you about today. One is it requires cognitive effort. You have to actually, even though it's just a little bit, a click takes effort. And because effort is normally what economists call present biased or present focused, it looms larger than it should relative to the benefits, which are long-term. The other thing is, if we're not sure of what we want, we have to spend effort to decide, to process the various information. And that also is a barrier to adoption. And this can lead to inconsistencies. And my favorite version of this would be people who actually are incredibly averse to adding a contact tracing app, and at the same time have an app that has location tracking on and is recording every step they take. Now, I'll turn it over to Kellen, who'll talk about our research.
Yeah, so in our research, we wanted to look at several ways to increase adoption by just changing the choice architecture of these apps. So we had predictions that 4 factors would all increase adoption. One is just to make the user experience a little bit easier by requiring fewer separate actions in order to enable the features of the app. So I'll show you what that will look like in just a bit. Then we could also change the way we label the app's function. So whether we call it an exposure notifier versus a contact tracer, because contact tracing kind of emphasizes this negative aspect of being tracked, whereas using the word exposure notifier, as Google actually switched from using contact tracer to exposure notifier for their API. This sort of emphasizes the benefit of being notified if you are exposed. And then you could also change the sponsor. So maybe CDC is slightly higher in trust for most people. So maybe that would increase adoption. And then we could also change the way things are worded. So you can't quite use opt-in versus opt-out in this context, because there are privacy concerns about defaulting people into sharing this information. But we'll show you ways that you can just change the wording a little bit in ways that apps are actually doing to increase adoption. So we conducted 2 empirical studies so far, and we'll show some results from those. So the first is this large survey of 5,000 people. We got a representative, essentially a representative group of the US people. So all different ranges and demographics. And then we asked a scenario, which was the key measure of whether they would be willing to download an exposure notifier app if they were given the opportunity. And we also manipulated. So for some people, they saw that it was sponsored by the CDC. For others, that it was a Google Apple exposure notifier system. And then we also manipulated the label. So whether we use the term exposure notifier or contact tracer. And we measured a bunch of things like political party and their attitudes about COVID to see how that would predict willingness to download. And finally, we have a second study, which we just have some initial results from, but showing some really promising and huge effects, ways to increase adoption. So we did this by just mimicking exactly what it looks like to download one of these apps and then enable the features. So using the exact design that's being used by some of these apps, for example, the one being used in Virginia or the one that they just rolled out in Canada. We have 250 responses here so far, and I'll show you some results in just a bit. So first of all, in the big survey of 5,000 people, we asked questions about things ranging from political party to who they trust, whether they trust the president, whether they trust the CDC and the media, and how worried they are about COVID. So the average person across the survey, 53% of the people said they were willing to download the app. And those who were worried about COVID, those who had higher trust in the CDC, those who had lower trust in the president, and so on, were much more willing to download these apps. So each of these had a pretty large effect that together really add up to huge differences between people who are concerned about COVID and have high trust in the CDC versus those who don't. So if you take somebody who has all those characteristics, who trusts the CDC, who doesn't trust the president, and so on, the likelihood that they download the app is actually 88%, whereas if you take someone who has all of the worst characteristics that predict lower downloads, 18% are willing to download the app. And subtle changes can also make a difference. So just using the term exposure notifier increases adoption by about 3%, and using CDC rather than Apple Google when describing the app increases adoption or willingness to download by 2%. Finally, in study 2, participants were all on their phones. So it was mimicking the experience of actually downloading and enabling features on these apps. So we'll show you a video right now of what this looked like for someone in the study. So first you get the screen about welcoming to the exposure notifier, and then you get these choices about whether to enable notifications. You get this choice between logging, and it's either continue or don't enable in this case, and then whether you want to enable Bluetooth. So it really enabled, in order to use this app in the way that it's intended, you would have to enable all 3 of those features. So we were interested in, do people do this, and how can you change the way choices are worded to increase adoption? So here's one way that we thought we could increase adoption, was just by using an opt-out wording. So here on the right, you see the choice of whether to turn on notifications is framed as just continue versus don't enable. And continue is in blue, and it's on top, and it's sort of the response that most people choose when they're faced with apps like this. Whereas on the left, it's framed as an opt-in, so as if they do nothing, they actually won't enable the features, so you have to take the active choice of enabling in order to enable the features. So we thought that would reduce the willingness to adopt the app. So on the one on the right makes it seem like the status quo, exactly. And so some apps actually do use something more like what's on the left. And when you look at the actual results from our study of these 250 people, 28% only of those in the opt-in wording were enabled all of the features, whereas 75% in the opt-out wording. So this is just a huge difference. And just any app that does use the opt-in wording definitely should change if they want people to enable the features and be more likely to use the app in the way that's intended by the designers. And finally, we manipulated in the study one other aspect. So most of these apps have either 2 or 3 different choices that people make, opting into the exposure notifications and then separately opting into whether they want to enable or use Bluetooth. So we thought if you streamline that choice architecture by making it simpler, giving them all the same information, but just combining it into one all or nothing choice. So enabling Bluetooth and enabling exposure notifications on the same choice, that people would be more likely to do so. So on the left, you see what half the people saw, which is 3 separate choices for each of these different features of the app. Whereas on the right, you see all these rolled up into one big choice between enabling the features or not. And what you see in the results is that people were much more willing to enable all the features in the 1 screen version than the 3 screens. So it just makes it a little bit simpler for them to enable all the features and just kind of streamlines the way the choice is framed. As a result, people were more willing to download and enable the features. So those are the key results from what we found so far. In the future, we want to see if we can use this to improve the design of existing apps and to see whether we can also change the choice architecture to make people more willing to share positive test results if they do test positive for COVID on one of these apps. And then finally, one takeaway from the study is that results can have, that subtle changes to the choice environment can have a big effect. So thank you very much for your attention. And
let me just add one quick thing, which is I think is a bigger lesson here, which is that subtle changes in choice architecture and user experience can have large impacts in lots of decisions, but particularly these adoption decisions. Another point, which I think is very important for us, is we had guesses about what would have the biggest effect, but it's really important to test several changes because some, like sponsor, which we thought would have a larger effect, turn out to be small, and others like opt-out wording will have large effects. So I think we actually think empirical evaluation of our intuitions and what respondents tell us is very important. Thanks a lot for your attention. We also want to thank Nathaniel Posner and Crystal Week, our co-authors, and Simon Zhu, who's been a great research assistant on this, and of course, again, the Columbia-IBM Center for Blockchain and Data Transparency for funding. Our email addresses are there, as are our Twitter handles. Please get in touch.
My name is Chen, and I'm from the computer science department. This talk is about an axiomatic study of block rewards in terms of their robustness against certain strategic manipulations. This is joint work with Christos Papadimitriou and Tim Roughgarden. So let me remind you very quickly that in most proof of work blockchains, there is this crucial component which decides how we allocate this so-called block reward to miners at the end of a block. Usually this is done by giving the reward, let's say $1 to the miner that solved the crypto puzzle first. Now, if we only care about the expected rewards, then this is the same as giving each miner a reward that is proportional to the number of hashes performed by this miner. This is why in the rest of the talk, I'll refer to this mechanism as the proportional reward rule or simply the proportional rule. The questions we're interested in are, is this proportional rule good or bad? If it's good, is it optimal? If it's optimal, in what sense it is optimal? Now, clearly these are open-ended questions, and even to approach these questions, one need to first think about, what are the desirable properties a good reward rule needs to satisfy. So part of the contribution of our work is to identify and formulate mathematically a number of such properties. These properties capture, reward rules that are robust against certain strategic manipulations from miners. Okay, So let me start with the definition we follow. A reward rule is any function that maps a profile of hash rates to rewards. Here, hi is the hash rate of miner I, and xi of h is the award that miner I receives at the end. The only condition we impose is that the total reward, the sum, needs to be at most 1. When it's exactly 1, we say the rule is budget balanced. So in this framework, in this language, the proportional reward rule is captured by this equation. Miner I at the end receives hi divided by the sum of hi's. Now you can see that the definition of reward rules is very broad. So we allow basically every function that looks like this. This brings up this very natural question. Isn't proof of work intrinsically proportional? If there is a reward rule that is not proportional, can you still implement it under the proof of work framework? Now, the answer to this question is, at least in principle, we can implement reward rules that are not proportional. So here is an example. So instead of terminating a block when a solution has been found, we can terminate a block when only after a sufficient number of solutions to the crypto puzzle has been found. Okay, for this, we can lower the difficulty of the crypto puzzle a little bit, but we only terminate the block when multiple solutions have been found. Using these solutions, potentially one can learn or approximate the distribution of hash rates from the miners. And then using this distribution, we can apply any allocation reward rule we want, at least approximately. So this motivates us to investigate this whole space of reward rules. And here is our main result. It's a uniqueness result. It states that if we want a reward rule that satisfies all these 4 properties, which I'll go through next, then you have to use the proportional rule. Okay, so these are the 4 properties. The first one says that the rule needs to be symmetric or anonymous. Basically, the IDs of miners don't matter. If you permute the hi's, the outcomes will stay the same. The second condition says that the rule needs to be collusion proof, which means that no group of players or miners can combine their hash rates and strictly improve their total reward. The third property says that the rule needs to be Sybil proof, which means that no miner can create new identities and split his or her hashes and gain reward. The last one is what we mentioned earlier, the sum of rewards needs to be 1. And it's not difficult to check that the proportional rule satisfies all 4 of them. And it turns out that this is the only one that satisfies all 4 of them. Also, let me mention that if we remove any one of the 4 conditions, then there are other reward rules that satisfy 3 of them. Okay, with this, let me say a few words about future directions. The first one is pretty clear. What we have done is about the simplest setting with 1 single block. It's like a single shot game. Can we extend the result to the more general setting with multiple blocks? The second one is about social welfare, or this parameter of total hash rates contributed by the miners. In the current setting, the miners basically have hash rates hi, they either use it or throw it away. But potentially they pay, but in reality, they pay huge cost in producing hashes. So this make the setting become like an auction. We can make this connection formal, but it becomes an all-pay auction with this proportional rule. We're interested in understanding the social welfare extracted by the proportional rule, because the social welfare corresponds to this parameter I mentioned earlier, the total number of hashes performed by the miners. Okay, so how well the proportional rule is in this aspect. With this, I would like to conclude the talk. Let me just thank the Columbia-IBM Center and the Data Science Institute for their support on this work. And thanks very much for your attention.
Hello, and many thanks for the invitation. Also, many thanks to IBM for its support for blockchain research at Columbia. With my colleagues, Chen and Tim Roughgarden, we have been one of the teams that were supported by IBM. And actually, our student, William Brown, was supported by this grant. And the title of our project is Incentive Compatible Blockchains. We basically use the economic lens to understand better the design constraints facing blockchains. For my part, I want to talk about something else that I've been interested in, related to Nash equilibria and blockchain. Good. So, probably not needed, but here is a quick introduction to Nash equilibrium. Here is a Nash equilibrium. Basically, this is a situation where several entities, agents, have many choices, and the choices of each affect the well-being of everybody. So, in this particular case, for example, the mango would love to be at the bottom of the bowl, but it's playing best response. This means that as long as none of the other fruits moves, it's going to stay where it is. And the same is true for all other fruits, and that's a Nash equilibrium. So in a game, which is, as I said, a situation where everybody's well-being depends on the actions of everybody else, a Nash equilibrium is a situation, is a quiescent situation, an equilibrium where everybody plays what is best response to what everybody else is doing. So that's a very important concept. It is the standard solution concept in economics. That is the standard predictions that economists will make for any such situation. Economists will argue, and they are right, that this is the only rational way to play. If you are playing a game, you should be playing Nash equilibrium. Nothing else makes sense. Also, in 1950, John Nash, in his PhD thesis, proved that the Nash equilibrium always exists, and got the Nobel Prize for this 45 years later. So that's very reassuring, because in any such situation, there will always be an equilibrium. So these are the three good pieces of good news about equilibrium. Here are the bad news. Nash equilibrium may not be unique. There may be many Nash equilibria, and that's of course confusing, because I know that I'm supposed to play Nash equilibrium, but which? Also, they may be randomized. In other words, in order to faithfully play a Nash equilibrium, you have to literally flip coins in order to choose which action to follow. So that's also confusing, right? Also, if the game is complicated, we know there are situations where to find a Nash equilibrium is intractable. So this means that it takes inordinate amount of computation, thousands of years to find. And as a result, you can't expect a group of people, a group of agents to find it. So it may be inaccessible for computational reasons. So that's bad. However, okay, the troubles of Nash equilibria disappear when you design the game. Okay, it's like a civil engineer telling you that buckling is a very subtle, very difficult, intractable problem. Sure, that's why civil engineers over the years have learned how to design buildings that never buckle. Okay, so when you design the game, that's called mechanism design, what you want is to create a game that has a unique, pure, and obvious Nash equilibrium, okay? Which, of course, also has to be the outcome that the designer desires, okay? So the designer optimum solution. And the classical example of mechanism design is, of course, Roger Myerson's another Nobel Prize paper, 1980 paper, where he found that the optimum auction design, when you have enough information about the behavior of your bidders, is to create a second price auction with a carefully selected reserve price, okay? And this creates a game that has a unique, pure, and obvious to everybody Nash equilibrium, and this is fantastic for mechanism design. This is the objective, the goal of mechanism design. If mechanism design sounds a remote interest to you, it's not, okay? These days, all distributed software and system design, including blockchain design, is mechanism design. I'm going to tell you now a classical mechanism, blockchain mechanism, and you all know that. I call it the Satoshi mechanism. It's Satoshi Nakamoto's 2008 paper, where he described the protocol, the distributed protocol that we know as Bitcoin. We know the rules. Miners compete to crack the puzzle. The lucky winner gets to add the next block to the ledger and receives 1 Bitcoin in return. And this is such a, I consider it sort of, the masterpiece of distributed system design, because here you have a protocol that has been run for a dozen years by millions of people. And I don't know of a bug report, okay, that it seems to have been working exactly as the designer intended. Miners are incentivized to participate, to compute as hard as they can, and to add the block as soon as they crack the puzzle. In other words, they don't hoard and fork, okay, which would be detrimental to the health of the cryptocurrency. So this was a story for a few years until it was discovered that this protocol has unintended Nash equilibria. Because you see, the Satoshi protocol assumes, in other words, Nakamoto states in the paper without proof that as long as no miner has 51% of the computing power, miners will not hoard and fork. However, a year insider 6 years later proved that even a 40+% miner is better off hoarding. Okay, so in other words, there is a bug in the Satoshi protocol. Now, since then, science has progressed. I mean, this 40% is now 30-something, okay? So, but still, it is considered a very annoying bug in the protocol, but it's innocuous and not dangerous in the least, because there are no miners of such great power. There is an even more ominous result, more recent, that when it is planned to be done after a few years, the rewards come not from the Bitcoin, not from Bitcoins, but from transaction fees. In other words, if the rewards have more variance, because now it's a Bitcoin plus change, then it's going to vary a lot from epoch to epoch. Variance may incentivize even smaller miners to hoard. Okay, so this is very annoying. It's a bug, but it's a bug of the future. What I'm going to tell you about is that I and my collaborators discovered a current and present bug. Okay, so we know that may be happening. Okay, so and this has to do with energy. We call it energy equilibria. That's joint work with Amos Fiat, Anna Karlin, and Elias Koutsoukias. Part of the important part of the Satoshi protocol is the difficulty adjustment process. Okay, in other words, every epoch, every 2 weeks, the difficulty of the puzzle is adjusted in response to how much computation was on offer the previous epoch. So the difficulty is proportional to the supply of computation, of computational resources. And it turns out, very surprisingly, that there are Nash equilibrium, in other words, a unique unintended Nash equilibrium, in a special case, when you have only short horizon miners, when the miners want to compute for 1 or 2 epochs and then quit the business. But in these extreme circumstances, there is a Nash equilibrium that is not intended, that goes against the whole philosophy of the Bitcoin protocol, namely that miners will collude to manipulate the puzzle difficulty. In other words, instead of going as the protocol wants them, instead of going all in with all their energy, all their computational power, they will throttle back their computation effort. As a result, the next epoch, the difficulty will be lower, and then they will go to full throttle to exploit the low difficulty, okay? The low difficulty, and they're going to gain something in the process. Now, these equilibria, which is a unique equilibrium, in other words, that's not something, a proposal or a possibility, it's the only rational way to play. But it kicks in when it takes about more than half a Bitcoin to mine a Bitcoin. In other words, where energy is expensive. And actually, much of the past 2 years has been like this, okay? Now, this is for the special case of short-term miners, but even for ordinary miners, long-term miners, we prove that there are Nash equilibria that are not as extreme, but they do manipulate the puzzle difficulty and the difficulty adjustment process. And they're either mixed, in other words, they require miners to flip coins, which is not miner performance, or they're very bizarre. Okay, for example, call for miners to abstain every third epoch and so on and so on. And recall that these bizarre equilibria, which are unlikely to ever happen, are the only rational way for the miners to act. Okay, and looking back, we have seen that such behaviors, throttling back behaviors, may have happened. If you look at the history of puzzle difficulty in the past 2 years, when energy costs were paramount, this may have happened a few times. Okay, so this is the work that I want to tell you about. You know, why Nash equilibria are of interest to people who are interested in blockchains. What I want to finish with the use of Nash equilibrium in permission blockchains, which may be of more interest to you. So the idea is the following: that I told you about a few, you know, bad mouth the Nash equilibrium in several ways. Here's another one. The Nash equilibrium may be socially suboptimal. In other words, we are a group of people. We are engaged in subtle and complicated exchanges, and the only rational way to act is a way that hurts us. Okay, it does not achieve the social optimum. It does not maximize our total utility. And the example they exploit is, you know, they have a model in which there is a blockchain solution for the market. The solution should be adopted because adoption would maximize the sum of all utilities, and yet the Nash equilibrium is not to adopt the solution. Okay, so the Nash equilibrium is below the social optimum. That's in the business is called the price of anarchy. Okay, how do you know when the price of anarchy is high? In this case, it's very high. One of the ways you go about is modifying the game, modify the mechanism, and in this case by adding payments. Okay, but if you add side payments, it is well known that games with bad Nash equilibria become much more benign. In conclusion, my point is that blockchain design is in many ways, and in very strong ways, a mechanism design problem. This means that the resulting game, and so I mentioned a few papers that make this point, the resulting game between participants should have a Nash equilibrium that is good, and good means pure, obvious, and optimal for the designer, okay? And if the designer is a community, for the community. And doing this can be subtle and needs theoretical foundations, which is what we're working on. And thank you very much for IBM support and for your attention.